All right, we're starting by taking a look at how to solve this equation. 4 to the x plus 9 equals 135. This is building off of the work that we did yesterday. Now, yesterday we saw how to solve something like this, but in yesterday's example, we didn't have something added on to the end like this one does. So the first thing that you're going to want to do then is get the exponential part by itself so it's like the one that we did yesterday. That means getting rid of the 9. So step 1, subtract 9 from both sides. Then this problem looks just like the one we did yesterday. So if you did not yet get to this point, work it from here. So from here, in order to solve for the exponent, remember that we have a function that exists solely for the purpose of finding the value of an exponent. That's why logs exist. The logarithm tells us what the exponent equals, because when I rearrange this exponential into logarithmic form, it becomes x equals, because of course log always equals the exponent, log base 4 of 126. Now that we have this, we can calculate our value. Calculating this value relies on using the change of base formula. Remember, that is going to be log over log, and the base always goes on the bottom. So in this case, our base is 4, so you know 4 goes on the bottom. That leaves the 126 to go on top. This is then the calculation we're going to be doing. So you do log 126 over log 4. Little side note here before we go and figure out what that number is. We cannot simplify this. You have to do it exactly as it is. It's not like we can simplify 126 over 4. Each one's trapped inside of a logarithm. It doesn't work. We can't cancel out the logarithms. That also doesn't work. And so you calculate it exactly as you see it. So do log 126, divide it by log of 4. You should be getting an answer here of about 3.489. Now notice I gave 3 decimals here. You notice why?
Thousands.
Yeah. This one's specified to round to the nearest thousandth. Get in the habit of looking to see what do I round to, because it does change depending on the problem that you're dealing with at any given time. So now shifting gears, start by writing down this problem, and then we're going to talk about how we'd go about writing an equation to represent it, and then how to solve it. So once you have this written down, we're next going to take a little bit of notes that we're going to be using in order to be able to do this. And then we're going to come back and use those notes to answer this question. So into your notes, I'd like you to write this problem, this set of notes, this equation. This is what we're going to use to represent situations that involve compounding interest. You should notice that it seems very familiar to you. That's to be expected. Get it down first, then we'll talk about why. So you want to write down all the little details around it. And one of the details that I really want to draw your attention to is this R. Notice here it says the rate of change is written as a decimal. And an example is given of 5% being written as 0.05 instead. Do you remember how to turn a percent into a decimal? If not, this would be an excellent time to write down next to that, divide the percent by 100. Because that's how we turn the percent into a decimal. We divide it by 100. And you're always going to have to do that when you're given a percent. Now, there's a clue in that as well. Because our rate of change starts as a percent, that tells you that this is an equation you're going to use whenever something is increasing or decreasing by a certain percent. And that's like on a yearly basis or whatever like that. Now, in terms of that basis, how often do we do it? The number of time periods is ambiguous because this could be used for interest that's compounding every day, every month, every year. But I will tell you that T is most commonly number of years. Yes, it can be used for other things, but you will find it most commonly talking about the number of years. All right, so now we're going to go back to our problem that you just wrote down. Let's apply that equation to this case. So starting with our equation, you notice the first thing we write is A of t. So okay, I'm going to go ahead and start by writing A of t. A of t equals. Now the first thing I write after that is the p value. P stands for principal. That's a financial term that means what we start with. So what do we start with in this problem? 500. Yep. 500 is our principal. That's what we start with here. So then we do 500 and then the parentheses, the 1 plus the rate. Now's the tricky part. I chose this particular problem to start you off with because I want you to see the importance of turning that percent into a decimal. Because a lot of people will look at this and they'll see 0.25% and they'll say, oh, but it's already a decimal. Well, it already has a decimal in it, but it's a percent. And so we still have to take the percent and change it into decimal form. And that means dividing it by 100. So I'm going to take 0.25, divide it by 100. That gives me 0.0025. That's the number I then have to use. So every single time when you have a percent, you're going to have to divide it by 100. All right, now I go to the power of t. In this problem, t is going to be 8. But you'll notice that since I just plugged 8 in for t here in the exponent, notice t actually appears twice in this equation. So this is no longer a of t. I now need to change that to be a of 8. Because when I plug in t in one place, I have to plug it in every place. And remember that a of t is just notation. That means the amount after 8 years. It's just shorthanding that piece of information. Now, a little side note here. Some people end up wondering, why do we have to do 1 plus the rate? Where's the 1 come from? The idea of it is that every year we start with our whole, and then we're adding this amount. We're adding that 0.25%. So we have that 1 plus it there because we're saying start with the whole and then add that percent of it. All right, now, in terms of actually doing this calculation, step 1 of the order of operations is parentheses. In this case, do that parentheses work first. 1 plus the 0.0025 is 1.0025. Write out that line when you do these problems because it makes your job a lot easier. You're no longer having to keep track of a bunch of parentheses when you type in your calculator or something like that. You can now see what you're typing in. So next step, let's figure out what this actually equals. Remember, do the exponent first, then multiply. So since the exponent is the power of 8, we do that first. So do 1.0025 to the power of 8, then multiply that by 500. You should get an answer of about 510.09. Now, on this problem, I rounded out to 2 decimal places, but I didn't say what to round to. In this particular case, I actually would expect you to know to put it out to 2 decimal places. What are we talking about here? What does this answer represent?
Money.
Money. And we always round money to the nearest cent. So that's the hundredths place, 2 decimal places. So always go out to 2 decimal places if you start by talking about money. Now, having done that problem, we need to look at this problem's annoying little brother. Because here we're looking at the same problem, but what if the account is decreasing by 0.25% each year instead of increasing? What is that going to change? Well, on your paper, first of all, make note of the situation. Decreasing by 0.25%. Start there. And then when you have that written down, we can start taking a look at what do I do to that equation that I wrote the first time in order to make it go down instead of go up. And some of you already were thinking along the right lines. Because right now this is increasing by 0.0025. If I want it to decrease, that means I'm going to subtract the 0.0025 from 1. So basically it's saying I start with the whole and then I take away the 0.25%. So then this is our new equation for this situation. Go ahead and now calculate this value as well, so we can make sure you can get the right value here. Now, when you went and did this work, I hope the very first thing you did was do that subtraction, do the parentheses. By writing it out this way first, writing it as 0.9975, you keep yourself from having to worry about a bunch of parentheses and all that stuff when you go and type it in. Now it's just a matter of do the 0.9975 to the power of 8, and then multiply it by the 500. You should be getting an answer of 490.09. And again, because it's talking about dollars, yes, you want to round to the nearest cent. So take it out to 2 decimal places. So having done that, this is a nice template problem. All the other ones you do are going to be very similar. But I do want to continue practicing that. So here's a second problem. Again, I want you to write it down, but on this one, you can just write down the highlights if you want to. If you're not sure what the highlights are, write down the whole thing. We now are going to go and write the equation for it. Now, when writing the equation, of course, we start with a of t. In this problem, though, we know we are actually going to have a t value. We know how many years are going to pass. And so I'm going to go ahead and put that in at this point. So what is the value of t going to be in this problem?
60.
It's not 60.
42.
It's 42, yeah. Now, why is it 42?
Because you subtracted t from 42.
Yep. We are looking to see what happens at age 60, but we start this investment when we're 18. And so 60 minus 18 gives us 42. So it's actually going to be invested for 42 years. So we know it's a of 42 equals. Next up, the p-value. What is the value of p in this problem? Remember, p is principal, our starting value. Yes, it is 1,000. Next up, we do our 1 plus the rate. All right, what is the value of r in this problem? 0.11. Because I'm taking the 11% and I'm dividing that by 100. So 11 divided by 100 gives me 0.11. And then it's to the power of t. Well, we already talked about what t is. T is 42, so it's to the power of 42. And then once you have the equation, you can calculate the value. If you haven't done so already, calculate what this gives us. All right, so first thing you want to do the addition that's inside the parentheses. Now notice my final answer is the one that I'm rounding to the nearest hundredth. I didn't round it before then, though. So that's why I still have all the decimals in there. So you should be getting a final answer here of $80,087.57. Now, I want to take a moment and have you think about what this really means here. Compounding interest can be super powerful if you use it to your advantage. Let me show you why it's so useful here. In this particular problem, we started with $1,000 and we were earning 11% per year. After year 1, we made about $100 of interest. But in year 2, I made more interest than that because in year 2, I gained 11% of the original 1,000 plus that interest from the first year. So I got interest on my interest. And then the third year, you get interest on the interest on the interest. And it keeps on growing and growing. So that by year 42 here, in order to get to this amount, we made in interest alone, just by leaving it there, over $8,000. So the first year we made 100. Year 42 we made 8,000. That's the 8,000 is just the gain that we made to get to that point. Now, let's see what happens if you're really patient and want to leave it even longer. What if we got this gift from our very fortunate aunt here when we were born instead of when we were 18? Figure out how much you would have in the account at that point. All right, so in this problem now, the gift is given when we're born instead of when we turned 18. So everything else is the same. We still start with the same amount of money. We're still earning the same rate each year. And so when we go to write our equation, everything is the same except instead of being there 42 years, this one is going to be in there for 60 years. And then this is the calculation. So let's do 1.11 to the power of 60, multiply that by 100. When we do that, we find that after 60 years, this is worth $524,000 $57.24. Now again, let's think about that meaning. Remember, at the end of year 1, we earned about $100. At the end of year 42, during that 1 year, from year 41 to year 42, we earned about $8,000. Here, going from year 59 to year 60, if you did that calculation, you'd find that we just went up by about $50,000. So we have done nothing over that year other than just leave that money alone. We just let it sit in there and grow. And we made $50,000 by just sitting there and leaving it alone. Which sounds like, hey, great, I didn't have to do any work. But the thing is, though, be aware that in order for you to take advantage of this, you actually do have to do a lot of work. And it's some of the hardest work we do. Because back here, when you got the $1,000, you have to leave it invested. If you get that $1,000 gift and you say, cool, I'm going to go get a new phone. Well, then in 60 years, you have a little pile of technological dust, and that's it. If you put it into the investment and you leave it there, you have over $500,000. The hard work happens at the start. The hardest part is putting it in and not touching it, because it's really tempting to reach in and touch that. But the goal with investing is normally put it in, invest it, and then forget you have it. Leave it there. Don't touch it. It's not an option to pull it out until it is time. And with something like this, the time to pull it out is normally when you retire. And you've decided when that is, for instance, at age 60, only at that point will you then go and access it. And if you've done all your investing really well, you won't even pull it out. You'll just live off the interest. And it'll keep growing as it did before, but you'll just live off the interest that it makes you each time. And so it's like you got a lifetime income just sitting there. Now, most of us don't have an aunt that's going to drop $1,000 into an account for us when we're born, right? But right now, many of you are at the point where you're starting to work. Take a little bit of that money that you make from work, put it in an investment account. Or, even better, you go on, you're really successful, you're making some good money, go be that aunt or uncle for somebody else.